right, so Unit 5 test is upon us. It is tomorrow. It will be 57 points. There will be 12 total questions. Some of them are shorter than others. 3 of the questions, I will say, are what I call thinker questions. So questions that you've never seen before on any other practice, but they're using all the same information we've been covering in Unit 5. You just kind of have to think outside the box a little bit. So I'd say there's about 3 thinkers on there. They're generally towards the back of the test, so maybe like the last 3 or so. Now there is one question. It's broken into 6 parts. Okay, there's one question broken into 6 parts. Don't get used to this. Okay, don't get used to this, but it is multiple choice. Okay, so we added a little bit of multiple choice in this one, so it's like just a few multiple choice in the question. Okay, do not get used to multiple choice on a test. This is probably never going to happen again. Maybe one more time, we'll see. But in general, we don't really do that in chem because I like to really make you think. So, but we're going to have a few of those, which, you know, are still a little tricksy. But, yeah. So that's our deal for test tomorrow. Mr. P, what am I going to have on my test tomorrow? You'll be given this exact periodic table. This is literally a picture of the one I printed off for you. Okay? So when you waltz in tomorrow, I'll be tossing tests on desks. So you'll have a test. You'll be face down like this. And as long as your stuff is away, you can just kind of gently pull off that back page. Here it is, that periodic table up there on the board. And you can write all over this thing. Okay? You will turn this in at the end of the test. I won't grade anything on here. In fact, I barely even look at them before I recycle them. It's just like, let's say Abby works out a couple of answers to the problems on her periodic table. I then don't want that in her backpack out and about in the open world. So I just collect them for that reason. So there's really no other reason why I collect them other than that. But yeah, you'll just turn it in a big pile up here on the right with everyone else's periodic tables, and I just recycle them right away. So, but yeah, you can write all over this thing. This is for you. It's also blank on the back in case you need it for scrap notes of any kind. Feel free. And I made the staircase a little juicier right before I printed this off, just so it's a nice dark line. It's no questions about it. Okie dokie. So that's what we'll have tomorrow. Let me see here. Let's talk about the concept map. I'm just going to highlight a few things about your concept map here. So you have this printed off in front of you. It's hole punch, so you can save it if you want to. So absolutely know all the different sections of your periodic tables, okay? You should be able to tell me what a group is, what a period is, and what it means for 2 elements to be in the same period or the same group. If 2 elements are in the same group, what do we know about those 2 elements? What do we know? Yeah, they're going to be really similar. They're going to be like siblings, okay? So Izzy, I had her older sister Faith. They do not look exactly the same, but I could definitely tell that they're related, okay? In the same way, elements in the same group, they're not going to look exactly the same. They won't have all the same properties. But you should be able to kind of look at them and be like, okay, yeah, I can tell those elements belong in the same group. Like the alkaline metals, they're all generally shiny. They're all generally soft. They're all generally explosive in water. Some are more explosive in water than others. Some are a little bit softer than others, but you get the idea. Now, elements in a period, will those always be similar? So like Krypton versus Potassium, they're both in period 4. Are those going to be similar? Are they? No, not at all. Okay, 2 elements in the same period could be as different as you could possibly get. Like Potassium versus Krypton, you couldn't get any different than those 2. Okay? Shiny, explosive metal with 1 valence electron versus an inert, noble gas that doesn't do anything and has 8 valence electrons. But what we'll see is every time you start a new period on a periodic table, a row, you start with a large, shiny, explosive metal. And then you slowly work your way across as the atoms get smaller and smaller and smaller, and you eventually will find yourself, hey, this is a really reactive non-metal called a halogen. And hey, this is a totally unreactive noble gas. And then all of a sudden you add 1 more proton to Krypton, let's say, you get to rubidium, and then you have a shiny explosive metal all over again. Okay? So the regular repeating pattern, as you will. And you need to be able to tell me, hey, if I describe an element for you, you should be able to tell me whether it's a metal, a non-metal, or a metalloid. Okay? And if I ask you, hey, Workman, what do you know about metals? What's the thing or two you could say about a metal in general?
Metal is a conductor.
Yep.
And it gives away.
Yeah, they tend to give away electrons. He could have also been like, they're usually shiny. Not always. They're usually pretty shiny. They're usually malleable. You can bend them without breaking, that kind of thing. You'd be able to do that same for nonmetals, all that good stuff. History. There's not a whole lot of history, okay? It's basically just Mendeleev. You should be able to tell me a lot about Mendeleev, though. What are some things we know about Mendeleev? I can think of at least 3 things. What?
Made the first periodic table.
Father of the periodic table. What else do we know about him? He was Russian. Oh, yeah. But what in terms of what he contributed to science, you're totally right there. He was totally Russian, and he looked like it, too. What else did he do? What do we know? Yes, Paul?
He left blank spots on the periodic table and was able to predict their properties.
Right. So, like my uncle who steals the last piece of every puzzle that we put together, when we're missing that piece, we can be like, all right, I don't know exactly what it looks like, but I can tell you several things that are probably true about it. In the same way, he left blank spaces on the periodic table, like, I haven't discovered this element, but I'm pretty sure it'll be like this. And so he's able to predict characteristics. How do he arrange the elements? Properties and atomic mass, right? So he put them together based on what was similar to others. They also were all in order by atomic mass. That's key. What's the main tweak we've made to our periodic table today? Yeah, elements are in order by their atomic number, or you could say protons. Yep. So it's still pretty similar. I mean, there are a few exceptions every now and then. For example, Krypton has 36 protons, but it actually has a higher mass than... Argon has 18 protons, but it has a slightly higher mass than potassium, which has 19 protons. So there's an exception to that every now and then. But generally speaking, the order that Mendeleev put them in was pretty similar to the order that we put them in, but not exactly the same. Electron configurations. You better be able to do those in your sleep. So if I'm like, potassium, you better be able to give me 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. You better be able to do that in your sleep. Okay? You don't have to do it quite that fast, but as long as you can read it off your periodic table. Or if I was like, hey, what element is 1s2, 2s2, 2p6, 3s2, 3p6, 4p1, or 4s1? You should be able to tell me like, oh, that's potassium. And if I was like, hey, what element's configuration just ends in 4s1? You're like, oh, that's potassium. If I was like, hey, what does potassium's configuration just end in? You'd be like, oh, that's 4s1. Okay, yeah. Like there's a lot of questions I could ask you there. Just be ready for that. Remember, the d orbitals are always one behind, so you go 4s2, and then you hit the 3d. And if you get to 5s2 after that, you'll hit the 4d. So watch out for that. So on your periodic table, like, hi, my name's Becky. I'm in 3rd period, and I just sat down to take my test. You know, you can pull up that periodic table, and you can be like, yeah, oh, hello. That's not what I wanted to happen. You can be like, no, stop it. I want my markers to work. There we go. You'd be like, yeah! I'd be like, that's the piece of it. I'd be like, woo, piece of it. Like, you can do all that if you want to, okay? If it helps you. You don't have to, but if you want to, you can. Oh, yes, trends. We got to know trends. This is very important to me. You need to be able to tell me, if I ask you to compare any atoms, or a group of atoms, you need to be able to tell me which one's bigger, which one's smaller. And not just that. You must be able to tell me what is physically true about the atoms that causes them to be bigger or smaller. Let's talk about sodium versus potassium, element 11 versus 19. Which one is bigger and why? Yes, potassium? Why do you say that? What is physically true about that atom of potassium that makes it bigger? You're right, it is potassium. What's the case? What's that? That's true. More mass doesn't always make something bigger. That is true, but it doesn't always make something bigger. So, for example, Krypton has more mass than potassium, but it's smaller in size. What makes potassium bigger than sodium? Yes, Paul?
It has one more orbital.
Not orbital, but I would say energy level, or we can kind of call that a ring. Yeah, so here, let me illustrate this. Let me go ahead and draw this. Okay. Here is what a sodium looks like. Tiny little nucleus. 1, 2, 3 rings, or energy levels. Hey, Mr. Pilcher, how do you know that sodium has 3 energy levels? How do you even know that? It's in the 3rd period, the 3rd row. Okay, that's how I know. Okay, every element in the 3rd row has 3 energy levels. Okay, so that's sodium. And look, here is potassium. It's in the fourth row, and so it has a fourth ring. And so once you draw it out, it kind of is obvious. Like, oh, yeah, that's clearly bigger. Like, it has another energy level. And so as you go down a group, elements are getting bigger and bigger and bigger because you're adding an energy level every single time you go down a group. Okay? Not bad. Now, what about potassium versus krypton? They're both in the fourth period, so they both have what? 4 energy levels, right? So they would both be drawn like this. I know this is oversimplified, but they both be drawn like this. What is different about krypton that causes it to be smaller? You want to try this? Yeah, that's right. So we got like a lonely little electron out here, let's say. And potassium has 19 protons pulling on that electron. But krypton has 36 protons pulling on that electron. Or electrons, depending on how many are out there. So as long as you're not adding a ring, okay, the atom with more protons will be smaller because it's going to pull on the electrons, those valence electrons on the outside, harder. Okay, it's going to pull them tight. And you need to be able to explain it. And some people, like maybe Izzy just draws pictures and barely labels them, just let me know the idea. And maybe Parker just goes like full sentences, or maybe Mia just gives me bullet points to explain it. But however you want to explain that is fine. You just got to make it clear to me that you know what's going on at the atomic level. Okay? All right. Let me see here. Now, other trends, the reactivity trend is probably the hardest one for people, I think, because they mix up with atomic size all the time. Here's a little thing I'll say. Metals get more reactive as they get bigger. Okay, so as they get bigger, they get more reactive. So francium, that's why it's so reactive, is because it's huge. Okay, non-metals get more reactive as they get smaller. So fluorine is super reactive because it is a tiny non-metal and it desperately wants one more electron. Remember how non-metals gain electrons to become anions? Fluorine is oh so desperate for it. Okay. Now, how come I didn't say helium? Helium's even smaller than fluorine. How come I didn't say helium's the most reactive non-metal? It's a what? It's a noble gas. What do we know about noble gases? What does that mean? They're in there. They don't do anything. They don't react. You got it. You got it. Yeah, so another way it says that noble gases, how many valence electrons do they have? 8, that's right. So they're not reactive. Noble gases electrons are never used for what? They're never used for... What are those valence electrons used for if there's a reaction? Bonding! Yeah, that's right. So the valence electrons are not used for any bonding, okay, in a noble gas. And then the number of valence electrons, yeah, you should know that trend, all that good stuff, nothing too crazy there. Yeah. And you should be able to tell me all about the different sections on the periodic table, especially the ones we emphasize. So I'm going to go ahead and just do a little practice here. Let me see here. Doink, doink, doink. There we go. Okay. What is the name for this section right here? Transition metals. Love it. What about these guys? Oh, hello. Stop that. Oh, goodness. This is going to drive me nuts. What about... Oh! My smart board's being so saucy. What about... Oh! My smart board, please! Please work. Will the black marker work? What about these guys down here? Earth metals. Not bad, not bad. What about these guys? Alkaline earth metals, okay? What about these guys? Alkaline. Hey, what do we know about the alkali metals in general? They are super reactive, okay? Now, I'm not super picky about spelling most of the time, but I will be pretty picky if I ever ask you a question where the answer is like alkali metals or alkaline earth. You do need to be pretty clear in your spelling there, because if you're not really clear, because they're so close together, I can't tell if you know which one is which, and so I'll have to mark it wrong. Does that make sense? So, again, normally not too picky about spelling, but I'll be forced to be picky. Alkali versus alkaline earth. Okay, so watch out for that. What about these guys? Noble gases. Tell me everything you know about noble gases. How many valence electrons? 8, except for helium. Reactive, not reactive, kind of reactive. Inert means not reactive. Not bad, not bad. Okay, all right. At room temperature, they're all what state of matter? Gases. What about these guys? What's their group number? 7. How many valence electrons do they have? Reactive, not reactive, kind of reactive? Very reactive. Okay. Okay, what if I asked you, like, hey, are these malleable? The halogens, are they generally malleable? Can you bend them without breaking them? What is known for being malleable? What kind of elements? Metals, right? And so non-metals are known for being rigid. Okay, if they are in solid form. So, for example, iodine is solid at room temperature. If you try and bend that, it'll just snap right in half. Yuppers. All right, not bad, not bad. Feeling pretty gravy about this. Okay, well, you guys, this is your life now. Towards the end of the period, I'll let you guys look at an answer key if you have your review sheet done, okay? And I'll also be distributing a few puzzles, so I got like logic reasoning puzzle number 3, I got a crossword puzzle that covers a lot of the same material, if you kind of would prefer to study that way. Whatever floats your boat, that answer key that's pink on your desk or below the video for you guys at home is for logic puzzle number 3, okay? So I'll be around to check in, and then for those of you guys who have been absent here or there, I'll be checking in with you as well. All right, let's go get them.